Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to talk about this circuit. We're going to design R1 in this circuit in order to having a current of 0.2 milliamp with these assumptions. In this particular video, first I try to use handy calculation in order to get the value for R1. Then I'm going to switch to LTspice, use an NMOS model, how we can define a new model for these assumptions, and then use the .op for DC analysis to see the result for I drain with that R1 value that we previously calculated in the handy calculations. But before we get started, smile because it make you feel relaxed and calm and happy for this video, and it causes you to make the most out of this video for you guys. And if you're new here, please give me a thumbs up, hit that subscribe button and also the notification bell, so whenever I upload a new video you'll be aware of it. Without much further ado, let's jump into it. So in this problem, I'm going to calculate R1. First of all, we have to assume that the transistor works in what region. This M1 transistor, it's a diode connected transistor, and the gate source voltage of this transistor and the drain source voltage are just the same, or in other words, the gate drain voltage of this M1 is connected together, so the gate drain voltage is equal to 0, which is less than threshold voltage. And if the gate source voltage is greater than threshold voltage, so these two conditions yields that the transistor M1 works in saturation. And as a result, I have this assumption that the transistor works in saturation, so this is the drain current for transistor works in saturation, 1 divided by 2 mu n C oxide W over L times VGS minus V threshold to the power of 2. With some simple mathematics, you can get the result that gate source voltage equals to square root of 2 times I drain divided by mu n C oxide W over L plus V threshold out of the square root. So the gate source voltage is equals to square root of 2 times I drain. I drain equals to 0.2 milliamp, and don't forget that this current goes through this NMOS. All of this current goes through this NMOS because the gate current equals to 0. You better keep that in your mind. So divided by mu n C oxide, this is 180 microamp divided by volt square, which is 0.188 milliamp divided by volt square, and these 2 milliamps are cancelled out, times W over L, which is this value 25 divided by 1, so plus V threshold, which is 0.4. If I use my calculator, I can get the result that the gate source voltage for this problem equals to, let me get this right, okay, 0.698. So this value is greater than threshold voltage, and in combined with this gate drain equals to 0, so the device works in saturation. Our assumption is completely right to get this formula for drain current. And finally, have this as an gate source voltage. We can now calculate the R1. How we can calculate it? By using a KVL in this route. So R1 equals to VDD minus gate source voltage divided by I drain. So VDD, I forgot to mention that VDD equals to 1.8 minus 0.698 divided by I drain, which is 0.2 milliamp. So this is about 5.5 kilo ohm for this resistor. This is the value for R1. Now I'm going to use this calculation and go through the LTspice to simulate it to get a better intuition. This is the LTspice, and by using some hotkeys you can accelerate your process of simulation. For example, you hit P and you can choose your component. I'm gonna write NMOS. Use NMOS 4 because with this NMOS you can change its model, what model you like. Hit R for resistor, hit V for voltage, and hit W for wiring your connections, and hit G for ground. Don't forget the ground, and try to connect gate and drain of this NMOS, and try to connect body and source of NMOS. Right click 1.8, and this one is 5.5 kilo. And for this NMOS I had to define a new model. Hit dot and use dot model, and you can now name your model. For example, my NMOS as a name, this is just the name of your model, and use NMOS KP for mu and oxide, which was 180 micro, and VT0 as threshold voltage, which is 0.4, and lambda for this particular problem equals to 0, which is lambda, because we neglect the channel length modulation. That's it for your NMOS. I'm gonna put it right there. And now you had to choose this name for this M1 as a model. So this is going to be my NMOS, okay? And now just choose the length and W, the length and width. This one was 1 micrometer and this one was 25 micrometer. And as you can see, the name of this M1 is changed to my NMOS. You can hit a space to fit your window in LTspice, and now hit dot for the analysis. I'm going to use operational point because I'm going to see the result for I drain, which is verify my problem, and use dot op for that simulation. And you can just hit this run, and there we go. You can see the result for I drain. What is the result? As you see here, I drain of M1 is this value. This is actually 200 microamp or 0.2 milliamp for this drain of this drain current of this transistor, which is clarify our calculations in handy mode. This is a really great idea to get the better intuition for you guys, and I'm using just simple modeling for in LTspice in order to get this feeling how we can relate our handy calculations with the simulation result. It is better if you're new in electronic to start with some simple simulations and find the relationship between your handy calculations and simulation results. Okay, I hope you enjoyed this video. If that's the case, please give me a thumbs up and share this video with your friend.